Every single model you have ever used or ever will use is a probability machine. When a classifier tells you an email is spam, it is not saying this is spam. It is saying there is a 97% probability this is spam. When a regression model predicts sales of 2 million, it is not saying sales will be exactly 2 million. It is saying 2 million is the most likely value, given everything I know. Data science is not about certainty. It is about quantifying uncertainty. And the language of uncertainty is probability. Without probability, you cannot understand what a confidence interval actually means. You cannot interpret a p-value. You cannot grasp why your model is overconfident. You cannot even explain what accuracy really measures. In the last video, we talked about the 4 pillars of data science. Probability and statistics was the first pillar. Well, probability is the language statistics speaks. Let us learn the language. Probability has a few core rules. They are simple, but they are powerful, and everything else builds on them. What is a probability? A probability is a number between 0 and 1 that measures how likely something is to happen. 0 means impossible. 1 means certain. Everything interesting lives in between. When we write P of A, we mean the probability of event A happening. P of A equals 0.3 means there is a 30% chance of A. The simplest way to calculate a probability is to count. You take the number of outcomes you care about and divide by the total number of possible outcomes. P of A equals the number of favorable outcomes divided by the total number of outcomes. For example, what is the probability that you win the lottery? In a typical lottery, you pick 6 numbers out of 49. There is exactly 1 winning combination out of nearly 14 million possible combinations. P of winning equals 1 divided by 13,983,816. That is about 0.000007%. That number is so small it is almost meaningless. But probability gives you the tools to quantify exactly how meaningless it is. The first rule is the simplest. The probability of something not happening is 1 minus the probability of it happening. P of not A equals 1 minus P of A. This sounds trivial, but it is surprisingly useful. Sometimes it is much easier to calculate the probability of something not happening. Think about the World Cup. Let us say Brazil has about a 12% chance of winning the next World Cup. What is the probability that some team other than Brazil wins? You do not need to calculate the individual probability for Germany, Argentina, France, Spain, and every other team. You just use the complement. P of not Brazil equals 1 minus 0.12. That is 0.88, 88%. What is the probability that event A or event B happens? If A and B cannot both happen at the same time, we call them mutually exclusive, and the answer is simple. P of A or B equals P of A plus P of B. But if A and B can overlap, we need to subtract the overlap. Otherwise, we count it twice. P of A or B equals P of A plus P of B minus P of A and B. Here is a real example. You follow a sports account on Instagram. Looking at their content, 40% of posts are about football, 30% are about basketball, and 10% cover both sports in the same post. What is the probability that a random post is about football or basketball? P of football or basketball equals 0.4 plus 0.3 minus 0.1. That gives us 0.6, 60%. Now, what is the probability that A and B both happen? If A and B are independent, meaning one does not affect the other, then P of A and B equals P of A times P of B. If you flip a coin twice, the probability of getting heads both times is 0.5 times 0.5. That is 0.25, 25%. But here's where it gets interesting. Most events in data science are not independent. Whether a customer buys depends on what they browsed. Whether it rains tomorrow depends on whether it rained today. Whether a patient recovers depends on which treatment they received. When events are not independent, we need conditional probability. Conditional probability is arguably the most important concept in all of data science. If you understand this, everything else clicks into place. P of A given B, written as P of a vertical bar B. This is the probability of a happening, given that we already know B happened. Let me make this concrete. Imagine a data set of 1,000 job applicants. 600 have a degree, 300 got hired. And of those 300 who got hired, 240 have a degree. What is the probability of getting hired? 300 out of 1,000. That is 0.3 or 30%. But what is the probability of getting hired given that you have a degree? Now we are only looking at the 600 people who have degrees. Of those, 240 got hired. 240 divided by 600 equals 0.4, 40%. The condition changes the denominator. That is the key insight. When we condition on B, we shrink our universe to only the cases where B is true, and then ask about A within that smaller universe. The formal formula is P of A given B equals P of A and B divided by P of B. Conditional probability is everywhere in data science. Every model is essentially estimating a conditional probability. A spam classifier estimates P of spam given the words in the email. Understanding this changes how you think about models. They are not black boxes making decisions. They are probability estimators. Here is a well-known example that confuses almost everyone. A disease affects 1 in 1,000 people. A test for the disease is 99% accurate. Meaning, if you have the disease, the test will correctly say positive 99% of the time. You test positive. What is the probability you actually have the disease? Most people say 99%. The test is 99% accurate, and I tested positive, so I probably have it, right? Wrong. The answer is about 9%. How is that possible? Let us walk through it. Take 1 million people. 1 in 1,000 has the disease. That is 1,000 sick people and 999,000 healthy people. Of the 1,000 sick people, the test correctly identifies 990 of them. It misses 10. Of the 999,000 healthy people, the test correctly identifies 989,010. But it falsely flags 9,990 as positive. So how many total positive results are there? 990 true positives plus 9,990 false positives. That is 10,980. Of those 10,980 positive results, only 990 actually have the disease. That is 990 divided by 10,980, about 9%. The rare disease means that even with a very accurate test, false positives overwhelm true positives. This is not a trick. This is how probability works. This is where Bayes' theorem comes in. Bayes' theorem tells you how to update your beliefs when you get new evidence. Here is the formula. P of A given B equals P of B given a times P of A divided by P of B. Let me translate each piece. P of A given B is what we want to know. The probability of A after seeing evidence B. This is called the posterior. P of A is what we believe before seeing any evidence. This is called the prior. P of B given A is how likely the evidence is if A is true. This is called the likelihood. P of B is how likely the evidence is overall. This is called the marginal likelihood or the evidence. The beauty of the Bayes' theorem is this. It tells you how to start with a belief, see new data, and rationally update that belief. Let us redo the medical test using the Bayes' theorem. A is you have the disease. B is you tested positive. P of A, the prior, is 0.001, 1 in 1,000. P of B given A, the likelihood, is 0.99. If you are sick, the test catches it 99% of the time. P of B, the total probability of testing positive, is the part we need to calculate. It is the probability of a true positive plus the probability of a false positive. That is 0.001 times 0.99 plus 0.999 times 0.01. That equals 0.01098. Now plug in these values in the Bayes theorem. We obtain 9%. Same answer as before, but now we have a systematic framework. This is the core lesson of Bayesian thinking. The strength of evidence depends on the prior. When something is very unlikely to begin with, you need overwhelming evidence to make it likely. Bayes' theorem is not just a textbook exercise. It powers real systems. Spam filters use Bayes' theorem. They estimate the probability that an email is spam given the words it contains. Each word updates the probability. The word lottery increases it. The word meeting decreases it. Bayes' theorem combines all of these updates into a final score. Search engines use Bayes' theorem. Given your query, what is the most probable page you are looking for? Recommendation systems use Bayes' theorem. Given what you have watched, what will you most probably enjoy next? So to wrap up, conditional probability is the foundation of every classification model. When you predict a label, you are estimating a conditional probability. Bayes' theorem gives you a principled way to update beliefs with evidence. The rules of probability help prevent common errors. The medical test example showed how ignoring base rates leads to wrong conclusions. In the next video, we are going to explore distributions, the shapes that probability takes in the real world. Why two companies with the same average salary can be completely different, and why the most important theorem in statistics makes the bell curve show up everywhere. Subscribe to the PlotLine if you want to understand the theory behind data science. I will see you next time. Thanks for watching.